Welcome to the video lecture. In this session I am going to explain various types of DC generators and their equivalent circuits. DC generators having the two main parts, one is the stator and another one is the armature. Stator having the field winding, armature having the power winding, that is called as armature winding. So armature is a rotating part, stator is a stationary part. In the inner periphery of the stator have the magnetic poles are there. In that poles field winding is provided. Maybe all the coils are connected in series, form a one winding. But you want to develop the voltage, it required magnetic flux. The magnetic flux source is either the permanent magnets or electromagnet. So here field winding is used for to set up the magnetic flux. Suppose based on this field winding is connections, based on field winding connection, it may be classified two types. One is called as separately excited DC generator. Second one is the self excited DC generator. In self-excited DC generator, maybe based on the connections, maybe it may be classified as this is the three types. One is called as shunt DC shunt generator, and second one is the series generator. Third one is the compound DC compound generator. This compound generator, once again based on the field winding connections, maybe there are two types. One is called long shunt, second one is the short shunt. Whether it is the long shunt or short shunt, based on the current direction, there may be called as, there are two types once again, that is called as cumulative compound or differential compound. Whether it is cumulative or differential, it decided by their characteristics. Even the cumulative compound, there are based on the characteristics, it can be classified with three types. One is called as over level and under level or flat level compound generators. This is the classification, but one by one I want to explain now. First of all, I am explaining about separately excited DC generator. In separately excited DC generator, field winding, this is the field winding, maybe it is denoted F and FF, general notation, and is separately excited by some variable voltage source. Once it is excited with some voltage, DC voltage current, the field current. And armature winding generally we are represented, yes, it is a rotating nature, it collecting from rotating parts, it collect the voltage through brushes, that's why it is a symbol of the armature. This is the generator. Outer terminals, here we have available terminal voltage. So this is the, once it is connected to the load, it delivers the current. Okay, this is the symbol of DC generator. You want to analyze the system, first of all, entire this generator is all the components converted to their equivalent circuit parameters. So maybe it is a winding is nothing but an inductor, but in DC, in inductor is excited, the steady state there it is active short circuit, that's why maybe their inductive nature equal to 0. So there is an inductance on the steady state, simply it acts as a pure resistor. So that resistance depends upon the length of the coil. Maybe it's open, it is the length, how much length and area of the cross section. Based on that, it offers some resistance. So that's why you can represent this resistance. Maybe it is the F and FF, and it is connected to the separate excitation through this voltage, field voltage. It passes the current IF. And this is the power winding. Armature winding is denoted with A and AA. This is the two terminals. Maybe it offers the, after combination, it offers some resistance. And also actually these coils are, this is the magnetic flux. Maybe this conductor armature is rotating like this, it is cuts the magnetic flux. At that time in this entire armature winding, it develops the voltage. That voltage called as induced voltage, simply denoted by, that is called as EZ. But their internal resistance of the winding is simply indicated here, RA. Yeah. So but RA general way, any other windings except the shunt field winding, any other winding, generally it is connected in series with the armature winding. So maybe interpole winding or compensated winding. What are the windings of special purpose? It requires some of the large size machines. So all the these windings are connected in series, that which offers the total resistance. Simple in circuit, the entire RA having that lumped resistance, combination of the series field and compensated winding, interpoles winding, what are the, simply can represented RA. And also here the brushes are there. Brushes also offer some resistance. Maybe it is very less. That's why sometimes we are showing some like a small battery in reverse of the actual induced voltage, or otherwise you can consider in the resistance. That's what the RA is the lumped resistance of the all the series windings of the this armature winding, including armature resistance. Now you can take it as it is the terminal voltage. Here you can connect to the load. Here it is connected to the load. Yeah, once you connected, it delivers current. It draws the that is drawn the current, that is called load current. The load current comes from the armature. This is the armature. What current is passing the armature winding, that is called as a armature current. What current is passing the load, that is called a load current. In separately excited machine, IA is equal to IL. Why? Because it is a single loop circuit. And it offers how to relate the characteristic equation in terms of both induced EMF and terminal voltage. We can apply KVL here. So based on the KVL, we can write it that. So minus plus. In any passive elements where the current is entered, generally are considered, that is called positive, and leaving them negative. Like this is the plus and minus. Across this one is the VT. Just you can apply the minus to plus combination loop equation. Minus to plus, I am taking as a plus, and plus to minus IARA voltages, and plus to minus VT equal to 0. Now the terminal voltage equal to, from this above equation, EZ minus IA RA. So this is the equation 1, maybe it is the equation 2. So by using these equations, you can analyze the internal currents and voltages and external currents and voltages. And also we are finding this is called as a field resistance. Here it is calculated, the field resistance RF is equal to applied voltage by Ohm's law. According to Ohm's law, we are calculating this VF by IF. We are getting the field resistance. By using these three equations, we analyze the circuits in the DC separately excited DC generator. And next I am talking about DC shunt generator. The main drawback of separately excited DC generator is the field winding is separately. You want to excite the, rather you want to develop the voltage, we need another DC voltage source to excite the generator. So, but after that, the scholars we can provide that how to their research we can get it, the self-excitation process they are identified. In this self-excitation DC generator, both suppose field winding and armature winding is connected in a manner. So suppose the field winding and armature winding connected like this, this is called as a parallel. So both field winding and armature winding are connected in parallel. That type of generator is called as shunt generator. Why? Because it is parallel to the armature winding. Armature winding. This is the symbol of representation of the DC shunt generator. Now we can replace the equivalent circuit parameters. Now we can redraw this diagram here. So I told already in the steady state and the in the DC analysis, enter the shunt field winding. It offers only resistance, so that is called as under steady state condition. In the analysis is the offers a resistance, that is called a RSH. And field armature winding, actually here the voltage developed. Why? Because under while rotating it cuts the magnetic flux, it develops the voltage, even though and this winding is the power winding compared to the field winding, shunt field winding. This in the high cross sectional area and also good conductors, and it offers less number of turns. That's why it offers very low resistance. So that is connected in series with the source. This is the equivalent circuit of the armature winding. Armature winding. So these terminals are connected to the load. This is the RL. Maybe it is a variable nature. Across this, we available voltage called as terminal voltage. This is the plus or minus. Okay. Now you want to what current once the connected to the load, high potential to low potential current is passing. So it is act as a source. It delivers the current, that is called as what current passing in the armature winding, that is called as armature current. It is the junction, it is splitted. Here the current is splitted based on the here the two resistors, load resistance and shunt field resistance are available. So across this winding here is terminal voltage. Based on that some current is passing here. This is called as a shunt field current. Here ISH is equal to, how can you calculate this one? Across the shunt field resistance, here available voltage called as a terminal voltage. So VT by and RSH, we are getting the ISH. Based on that, suppose you know that ISH value and VT, generally we are calculated this RSH value. Maybe it is called as equation 1. And based on the load resistance, it is also draws the current, that is called as IL. Yeah, in that junction, maybe I call some junction J. Here we apply the KCL, this KCL. So entering current is equal to leaving current, so that IA is equal to IL plus ISH. Here IA is entering, the both ISH and IL are leaving. This is the equation 2. And we have to relate the both induced voltage and terminal voltage. Just to write it the loop equation here in this loop and apply KVL. Here we can write it the same. So my 3 voltages are there, minus here actual voltage, and also what is the voltage developed in the armature winding, that is called as easy, and voltage drop of armature winding here where the current is entered, that is going to take in plus and minus. So apply loop equation, minus to plus I am taking as easy, plus and plus to minus automatically minus, and plus to minus and the voltage. This is the voltage equation, that's why all are in voltages. From this equation Vt is equal to Eg minus Ia Ra. This is the third equation. By using these 3 equations we can calculate the either internal voltage and their terminal voltages, like that currents. So this is called as a these are the equations. It is called equivalent circuit of this shunt generator. By using these equations we can analyze the all the internal and external parameters. Now coming to another generator, that is called as DC series generator. Series generator. Very simply, we observed in the DC shunt generator, actually DC shunt generator having the more number of turns, the shunt generator, the field winding having the more number of turns and less cross sectional area. So R as the shunt field resistance, always any resistance of the winding is depends upon the proportional to their length of the coil or length of the winding, and inversely proportional to the area of the cross section. So it is connected across the terminal voltage. So that's why RSH across we have to take the terminal voltage very high voltage. So but the aim of this winding is to set up the magnetic flux, not a, so that's why as possible you have to minimize their current. You want to take the low current, it offers exactly, it maintains the high resistance. For example, our terminal voltage is 230 volts. Here the it is the 230 volts. 230 volts. But I want to design for the 1 ampere field winding. At that time, it offers. For example, it have 230 ohms. 230 volts by 230 ohms. It draws only 1 ampere. So maybe it is the 2% of the actual rated current of the machine. So like that. So high 230 ohm resistance, very high resistance. So how it is getting out of the, first of all, more number of turns and less cross sectional, because less is nothing but denominator less is nothing but this value is more, and also overall RSH value, it is depends upon the their resistivity, the material constant, and L by A. So L more, RSH is more, A less, RSH is A more. So it is the material constant, maybe it is a copper or aluminum, it is depends upon the their resistivity is provided. Finally the RSH is given. So in DC shunt machine have the more number of turns, more number of turns are more, and also less cross sectional area. That's why shunt field winding offers the high resistance. But series field winding generator, it is designed like this. Why? Because it is connected in series with the armature winding. It is connected in series with the armature winding. So it's offer the so it carries the actual rated current. This is the IA. So IA is very high. That's why we are designed for the capable to the high current rating of the winding. So high current means high cross sectional area. So series field winding is proportional to L and inversely proportional to A, and RSC is equal to rho L by A here also. But LSC is very, suppose field winding, it is very less, and so that's why resistance is very less. Area of the cross section is more compared to the shunt field winding. So at that time also series field winding. So denominator is more, out of the value is less. So RSC is low. So it offers low resistance. It offers low resistance because of the more cross sectional area and less number of turns. That means the length is very less. So this is the RSC. And suppose DC shunt generator is always connected, operated under load only. Why? Because there is no load, it is acted as open circuit, that's why it is not working. This generator itself, it is running with the load. So here the what current is passing to the load, that is called as IL. Yeah. So here IL and what current is passing series field winding, that is called ISC. So you observe that DC series generator having only one loop. So we separate, we provide the equivalent circuit values. This is the RSC, field winding resistance, and armature winding having some resistance RA and a developed voltage, that is called as EG. These two are connected to the their load resistance. This is the RL. Now IL, and once you connected, high potential doper current is passing. So this is called as what current is passing armature winding, that is called as IA. What current is passing field winding, that is called as ISC, and what current passing through the load, that is called as IL. So in series generator only one loop is there and only one path is there. In any path only one current is available. That's why that is your load current equal to armature current equal to field current, only one current. So and also you want to calculate their external parameters and internal parameters, terminal voltage and induced EMF. Write the loop equation here simply. Where the current is entering, that is taken as a plus, minus, and plus and minus, here plus minus, minus plus, plus minus, plus minus, plus minus. You have to write the loop equation. Suppose minus to plus, I am taking a plus, easy, minus, automatically plus minus, minus to plus plus, then plus to minus, minus, IA RA, and minus IA RSC minus plus to minus VT equal to 0. So here actually this is the IS is equal to IA, that's why I'm writing like this. So VT is equal to EG minus IA into RA plus RSC. This is the one of the equation. So equation 1 and equation 2, here the 2. By using these two equations, we can find the internal parameters and external parameters, the problems, and analyze the mission. So I concluded that here what I observed in shunt generator. In shunt generator, generally the field winding connected in parallel with the armature winding. That's why across this field winding we are connecting the terminal voltage. So it isn't for the low current rating. Low current rating is nothing but low cross sectional area, and you want to set up the more flux, either MMF formula Ni. So more number of turns and less current is here NSH and ISH. Generally it gives the same flux. Like this here also series field winding, it offers some maybe it having some turns NSC and it was the ISC. So maybe set up the same flux for same rating. But shunt field winding carries the low current. Why? Because it is a low cross sectional area and more number of turns. It offers more resistance. In series field winding, very low resistance, and also it set up the flux. So next class I can explain the another self-excited machine that is called as compound generator. Based on the field connection, maybe it is classified into two types, that can be explained in the next class. Thank you.